anything from here.
All right.
Only your response.
So what we are talking about today is, so we are finally at the point, I think I've warned you guys that this class hits a point where all of a sudden everything gets really abstract. This is now, right? So section 4.4 going forward, this next bit of the class, this is the most abstract part of it, but also why linear algebra is so useful. So,
What was last week?
not as abstract as it's going to get. So, I'm going to remind everybody before we start, you're going to remind me anyway, we're going to talk about subspaces, and then we're going to use subspaces as a motivation for talking about the subject of 4.4, which is spanning sets. And we'll be talking about this today and tomorrow. So, first I want you to remind me what it means to be a subspace. So, given a vector space V, we're going to do lots of examples today. Given a vector space V, S is a subspace of V if what?
It has a zero vector if adding in the subspace keeps you in the subspace, and if scalar multiplication in the subspace keeps you in the
Okay, so the zero condition is not actually strictly necessary. That's implied by the scalar multiplication condition. So if 0 is not in there, it can't be a subspace, right? But if the scalar multiplication will imply 0 is in, because k could be 0.
0, and if it's 0, okay.
Okay, so closed under addition. Now I'm going to introduce you guys to some more, the book is going to shift to some more abstract notation here. So what that means in abstract notation is if U and V are elements of S, so this symbol right here, this little epsilon symbol, this is the set inclusion symbol. It means in or is an element of. Because it's annoying to write that down over and over again. So the way you would read this in English would be if U and V are in S, then U plus V is in S. Any two things you start with, you add them together, you stay inside the same set. Condition 2. If U is in S and K is an element of the real numbers. That is the same thing, and the book does this too if you go read the book. What that means is K is in the reals, or if you like, K is a scalar, is what that symbol means. If U is in S and K is a real number, then K times U is in S. So this is the condition of closed under scalar multiplication. Okay, so we're going to take this pretty abstract idea, and I'm going to define a very, very important subspace, and then we're going to show that it's a subspace. So it's sufficient to show that something is sort of a self-contained vector space if it lives inside a big space and it satisfies these two conditions. So let A be an M by N matrix. So A is just a matrix. Then there's a square, it could be rectangular. The null space of A. So the null space, somebody told me in the last section that Dr. Retzek didn't tell you what a null space was. I'm going to tell you what a null space is. The null space of A is the set of solutions to A times X is equal to 0. So the null space of a matrix is the set of vectors that when you multiply by A, they get turned into nothing. That equation always has a solution because the 0 vector always solves it. A times 0 is equal to 0. But there might be other vectors that happens for as well. So I'm going to remind you of some more abstract terminology that shows up in the book. So because it's annoying to write null space of A over and over again, people will sometimes write that the null space of A, they might use the shorthand null A to mean the same thing. And in set builder notation, what you would write would be the collection of vectors x contained in Rn that have the property that A times x is equal to 0. So this is set builder notation. Some of you have tried to use this on exercises. This is a shorter way of, instead of me having to write down some giant sentence, I can just characterize a set in terms of a rule that all the elements have to follow. You're in the null space of A if A times U is equal to 0. Okay, so we're going to make a claim now, and I'm going to try to link this idea of the null space up with the idea of being a subspace. Claim. The null space of A is a subspace of Rn. Okay, so we're going to prove that the null space of A is a subspace of Rn. In fact, it's maybe the most important subspace of Rn. So if you want to know why we're sort of doing the super abstract stuff here, and the way it's going to link back up to what we've done before, essentially, the whole goal of the next sort of 2 weeks of the class is going to be, we have one tool. One. We're doing linear algebra. The only tool we have is row reduction. It's like our hammer. If we can turn something into row reduction, we can solve it. So we're going to build this abstract stuff, and then all of the rest of the tricks are going to be taking abstract problems and turning them into row reductions. So that's kind of where the two-way street's going to be. So the secret of linear algebra and why it's so powerful is that many questions can be turned into row reduction. Okay. So this space in particular is a really nice one for row reduction problems. So what we're going to start with is we're just prove it's a subspace with the subspace conditions. So this is going to be abstract. I haven't written proof on the board in a while, so proof. So let's let C1, let's see, let's let U and V be in the null space of A. So I need to show that two things are true in order for this, what?
Is the entire purpose of this just to solve systems of linear equations?
No, you should think of it's backwards. The entire purpose of this is lots of stuff can be turned into systems of linear equations. Okay. Right? So you should think of linear equations as the tool that we're using to solve all kinds of stuff. So in the with what we've done today, I'll show you later that like integration and differentiation are just matrix multiplication.
Wait, and just to
No.
No. Ax equals 0. A can't have an inverse. I know that's not related to what we're doing, but just A can't have an inverse, right? Like you can't have A inverse for this. So.
There's no. The null. Okay. Null A always. This is actually an important point. Exists. Always.
Okay.
It's always got something in it. It's the set of solutions to Ax equal to 0. What solution is the solution that's always in the null space of A?
0.
0. And in fact, if the matrix is invertible, it will be the only solution to that equation. If A is invertible, the null space of A will literally be just the 0 vector and nothing else.
How do you have something that's not the 0 vector in there? What?
I'll show you.
Okay.
You want to start with examples first? We can do my examples, and then we can prove it. We're going to prove it, though. There's no dodging it. So, for example, let's look at A is equal to -1, 5, 3, 2, -10, -6. And I say, I would like to calculate the null space of A. So, the first thing I'm going to do is I'm going to take this problem and I'm going to write it out in its matrix equation form. The null space of A is the set of solutions x to the equation A times x is equal to 0. And if I wrote this out, not symbolically, but concretely, what that would mean is I'm solving the problem -1, 5, 3, 2 minus 10, -6 times x, y, z is equal to 0, 0. That's the actual concrete problem that we're solving when we're finding a null space. The collection of vectors x, y, z that make that equation true. Now, of course, because we have one tool, and that tool is row reduction, when I see that, immediately I want to turn it into an augmented matrix and row reduce it. That's all I can do. So, using augmented matrices, I could rewrite this as -1, 5, 3, 0, 2 minus 10, -6, 0. So I hit it with an augmented matrix. If you row reduce that, you end up with this. 1 minus 5 minus 3, 0, 0, 0, 0, 0. And we've solved this problem a bunch in here already. This is just solving a system of equations with augmented matrices. In fact, I look at that and I see free variables. The whole point of me pushing you guys to write this vector form of the parametric solution sets is going to happen right now. So what is the solution set to this? What are the free variables in this problem? X, Y, and Z. So either x2 and x3 or y and z. So these are free. If we write that down parametrically, what that means is, okay, so y, I could write the equation x minus 5y minus 3z is equal to 0. Since y is free, I'm going to write it as the parameter s this time. It's following the book. Z is a parameter t because these guys were free. And what that means is the solution set, x, y, z, has the form 5s plus 3t st, where s and t are real. And if you pull that apart, you get s times the vector 5, 3, 0 plus t times the vector 3, 0, 1.
Why is it 5, 3?
5, 1, 0. And so the claim is, for any choice of s and t, if you take your numbers s and t and you multiply them by these vectors and add them together, every one of these will have the property that if you multiply that by a, you get the 0 vector out. So the point of the linear algebra here is we've turned this abstract idea of the set of vectors that A destroys and turned it into a vector problem. And in fact, the s and the t don't even really matter. I could reproduce this entire collection of vectors just by saying, oh, well, this is a sort of thing called a linear combination, and so it turns out that the null space of A is all the possible linear combinations of these two vectors. So, in some sense, these two vectors are like the skeleton or the bones of the set. If I knew those, I'd know all the rest of it. So I've reduced this problem where I have an infinite pile of solutions to this to a very simple description in terms of two vectors. And this idea of taking complicated solution sets and pulling them back into descriptions in terms of collections of vectors is so powerful, we give this set a name. And this is actually the subject of what we're talking about in 4.4. This is called, I'm going to formally define this, but I'm going to say it now. This is called, this type of thing where we've got combinations of vectors is called the span. And this is what we want to do in 4.4. We want to take complicated collections of vectors and reduce them into very simple descriptions in terms of like basic elements. Okay, so this is the 4.4 idea. Now, not every span is a null space, But every single null space of any problem we've written down, you've seen this, right? Collection, some vector, plus a pile of combinations in terms of S and T or whatever the free variables are. All of these problems are solved the same way, and they all reduce to like some kind of fundamental set of solutions that you can then multiply. Okay, just because I am not totally convinced from my discussions in the last class that everybody knows how to check that something is a subspace, and because I'm going to ask you to do it, you should probably know how to check that something's a subspace. Null A is a subspace. I should point out that that was a good go. So, how do you prove something's a subspace? Close under addition. In fact, I might ask you to prove that the null space is a subspace. So the way this sort of argument goes, this is pretty fast. You let two vectors be in the null space of A. And then we want to check that U plus V is in the null space of A. How am I going to do that? I'm going to multiply by A and see if I can zero out. A times U plus V is equal to A times U plus A times V. Oh wait, but U and V were both in the null space of A. So A times U is 0, and A times V is also 0, and 0 plus 0 is 0. So when I took U plus V and I multiplied it by A, 0 was the vector that came out. And that's exactly what it means to be in the null space. So U plus V is in the null space of A. Likewise, so condition 2, we're going to check that K times U is in the null space of A. So let's let U be in the null space of A, K be a scalar. Then that means we really want to know if A times K times U is in the null space of A. So unlike matrices, scalars do factor out of matrix multiplications. So I could rewrite this as K times A times U, because scalars commute with matrices. But A times U is in the null space of A, so this is K times the 0 vector, which is the 0 vector. And that means that K times U is in the null space of A. And since you've checked both conditions, your conclusion is the null space of A is a subspace. So the null space of A is a subspace. One of the fundamental subspaces. All right. So what we want to do is we want to take the idea of what this sort of structure that we got from the null space, that you can take null spaces of these matrix problems and pull them apart into their basic vectors, and we want to take that idea and use it on lots of subspaces instead of just these specific ones. And so to do that, I guess I should probably remind you guys of something that we've stated in here a bunch of times, but maybe you haven't picked up. So now this is 4-4 material. So a linear combination of vectors v1 to vn. Now notice, I am not talking about vectors in Rn here. These are vectors in a vector space. Any vector space, matrices, continuous functions, polynomials, Rn, like anything can be vectors here. A linear combination of vectors v1 through vn is a sum of the form c1 v1 Cn, Vn for some scalars. C1 to Cn. I take my vectors, I multiply them all by scalars, I mash them together with addition. That thing that you get is the linear combination. This part of the class is heavily dependent on knowing the definitions. So when I say linear combination, that should be the immediate thing that flashes in your mind, right? You'll know that you've got this material when that becomes instant. So once we have the idea of linear combinations, I might want to look at all possible linear combinations. The span of a set of vectors v1, v2, up to vn is the set of all possible linear combinations. Of v1 through vn. Now, because that's annoying to write, we can use a mathematical description of the same set. So in sort of the mystic language of mathematics, you write the span of v1 through vn is equal to the set c1 v1 plus cn vn, where c1, c2, up to cn are scalars. So that's the set builder notation for it. Every possible linear combination of v1 through vn. And I'm going to write down some concrete versions of this now. This is pretty abstract. So for example, I might ask you, what is the span of the vector 0, 1, 0? And the way you think about it is every possible linear combination of that one vector. If you wrote that down, what you'd be writing is it's all c's times the vector 0, 1, 0, where c is real, which is all vectors of the form 0, c, 0. What sort of geometric object is that?
Line in the y-axis.
It runs along the y-axis, right? So it's a line, right? It's a one-dimensional, it's the span of a single vector is a line. It's every possible length of this vector plus all of its reflections in the negative direction. So it's a parametric description of a line. This is a line. A one-dimensional line sitting in 3D space. If I asked you for the span of 1, 1, 0 and 0, 1, 2, then you would write down C1 times 1, 1, 0 plus C2 times 0, 1, 2, where C1 and C2 are real. What's that?
C1, then C1 plus C2, and then 2.
You could smash it together. So yeah, one thing you could do is you could just smash it together as C1, C1 plus C2, 2C2. But what geometrically, what is that?
Plane?
It's a plane. This is a plane, right? Because now what you're taking is you have two parameters. The vectors are pointing in different directions, and so you're looking at a two-dimensional plane in R2 or in R3. Now, to give you the idea that spans are more complicated than that, let's take a look at this. What is the span? Now let's suppose the vector space V is the vector space of continuous functions. And S is the span of the vector 1, the vector x, and the vector x squared. continuous functions are a vector space. I can take 3 vectors in that vector space and mash them together with linear combinations. What do I get out when I do that?
C1 1 plus C2 x.
So you could write it concretely as the set of all things C1 times 1 plus C2 times x plus C3 times x squared. What is that collection of objects?
Parabolas.
All the, what, does it have to be parabolas? What if C2
Oh,
was
no,
0?
Could be a line.
So this is
Or-
the
Yeah.
Of all functions below x.
polynomials
Yeah.
of degree 2 or less. Okay. Lots of things are vector spaces. Lots of things can be thought of as spans. So the span of this collection of vectors is all of its linear combinations, which means every degree 2 polynomial can be thought of as a span. Okay, let's check my notes here and make sure I'm not losing track of what I want to do. All right, so let's talk about. Okay, let's do this. So one of the nice things about spans, about the nicest objects that you can work with in linear algebra, are subspaces. And it's not hard to show that the span of a collection of vectors is a subspace. One of the ways that it's pretty easy to see that is, what does it mean to be in the span? Well, you could let the vector u be equal to c1 v1 up to cn vn. To be in the span means you're a linear combination of v1 through vn. I could pick another arbitrary vector in the span, so d1 v1 up to dn vn. So that's a linear combination of the v's, that's a linear combination of the v's, and if this is going to be closed under addition, if I add them together, I should also get a linear combination of the v's. Probably I shouldn't be reusing v as a symbol here, so let's call that w instead. Well, don't you just c1 plus d1 times v1 symbolically, I think that's true. You add the vectors together and collect like terms. And notice that what you've produced here is a linear combination of the v's. It's a scalar times v1 plus a scalar times v2 plus a scalar times v3 plus so on to a scalar times vn. This thing that you got out is in the span of v1 through vn because it's a linear combination of those vectors, which means it's closed under addition. If you took a scalar k and you multiplied it by u, you would have k times this linear combination of the v's, but then distributing gets you kc1v1, kcnvn. So if you take a scalar k and you multiply it by a linear combination of the v's, you get another linear combination of the v's. This is scalar times v1, scalar times v2, scalar times v3, until you get out here to scalar times vn. This is also in the span of v1 through vn. Closed under addition, closed under multiplication means it's a subspace. So now we get to one of the more annoying pieces of terminology here, which is that span is used in at least 3 different ways in this material. So I want you to think of our first definition was the span of v1 up to vn is the subspace span of v1 through vn. It's the collection of all linear combinations, right? So the span of a collection of vectors is the subspace you get by mashing linear combinations together. I'm just repeating what I've already written there. If S is a subspace and every vector in S can be written as a linear combination of V1 through Vn.
Is this another definition?
It is a new definition. Yeah. If S is a subspace, and every vector in S can be written as a linear combination of V1 through Vn, we say 1 V1 through Vn is a spanning set for S. And 2 V1 through Vn spans S. How annoying that is. You got a noun version of span, a verb version of span, and a noun version of spanning that's in the opposite direction. So just to remind, like this, people get this confused. This is a noun, and it says it's the vector space that you get out from combining all the V1s through the Vn's. This is a noun, and it's the set of vectors that create the vector space. This is a verb, and it indicates the relationship that anything here can be written as a combination of these. I did not make up the terminology, so. Okay, so let me see if I can give some examples. Let's make them super concrete about this. So first, I might ask the following question. Question is 1, 2, 3, 3, 4, 5, 4, 5, 6 a spanning set for R3? Everything in linear algebra basically comes down to how can I translate that into a matrix reduction? Because we have one tool. So we're going to concretely start with we're going to start with this abstract question. We're going to feed it through vocabulary, and ultimately it's going to result in a matrix reduction. And since you've already written your one matrix reduction you have to do by hand for all time, you can just use computers to boil these things down if you get them on your homework, right? And on the exam for this section, I'll just give you word-reduced matrices to interpret. Okay, so what this question is asking is the following. For this to be a spanning set for R3, what that means is, given any vector, A, B, C, in R3, so an arbitrary vector in R3, does there exist, does a solution to 1, 2, 3 times x plus 3, 4, 5 times y plus 4, 5, 6 times z equals A, B, C exist? Are we guaranteed that no matter what vector I choose here, I can solve this problem? Because if I can, it means any arbitrary vector I write down can be written as a combination of these three. And if I can't, it means you can't.
Why is the whole vector x or x, y, and z just random variables?
Those are the scalars. Those are the coefficients. So if you want, you could think of this as being C1, the C1, C2, and C3
so
from before.
X, y, and z are arbitrary.
They're scalars.
They're arbitrary. They don't.
They are not. So what I'm gonna
Because usually x is like 1, 3, and 4, but you're using x as like.
Oh, do you want me to put it over here instead? Is this what your complaint
No,
is?
because usually x would be like the x variable is like 1, 3, and 4, and the.
Okay, I'm going to immediately translate into what you're doing, like immediately. Okay, so what equations do these give you? X plus 3y plus 4z is equal to a, right? If you were going to translate this into a system of equations, wouldn't this become...
But how did you know that, like, because all the matrices were separate, right?
Huh?
Don't they each have their own x, y, and z?
No. to ask if something is a spanning set is to ask specifically, like if I give you a concrete vector here, like 1, 9, 10, and I ask, can you come up with a linear combination of these things that produces 1, 9, and 10? I'm just solving the problem in general. If I write a general vector down, can I find things I can multiply these vectors by to scale them in different ways so that when I add them together, I get this as the output?
So if we
These will have A's, B's, and C's inside of them if this has a solution.
Okay, so this is basically, so those are like one big A vector, so it's like each.
I'm immediately gonna, this may be clearer once I do the translation step. So the first thing we're gonna write here is, this is the same as having written down 1, 2, 3, 3, 4, 5, 4, 5, 6 times x, y, z is equal to ABC. I've got one tool and it's row reduction, so I have to take my problems and turn them into row reductions. So what I'm trying to figure out is there a way I can scale these three vectors in some way so that some arbitrary vector that I wrote down here is produced? If I gave you a concrete vector, it would be very easy to see this question, but I want to solve all possible questions simultaneously. For an arbitrary vector, can I find an x, y, and z that will make these things combine into it? Necessarily, if the solution to this exists, x, y, and z will have a's, b's, and c's all piled up together inside of them. So I can translate this into a system of equations and then translate that into a matrix problem. But of course, we never work with this form. We immediately hit this with an augmented matrix. 1, 3, 4, A, 2, 4, 5, B, 3, 5, 6, C, because our only tool is row reduction of augmented matrices. And so everything turns into that. And you row reduce it. And what you get is, because you'll never have to do this, although you probably will have to learn how to row reduce abstract matrices. Wolfram Alpha will happily do this for you. This row reduces to 1, 0, minus a half, 0, 0, 1, 3 halves, 0, 0, 0, 0, 1.
How does it get rid of the A, B, and C?
It's an artifact of the algebra. And generally, if this had a solution, there would have been A's, B's, and C's over here in this column.
Oh, so if there was a solution.
If there was a solution, there would have to be A's, B's, and C's.
Oh, okay.
Right? It's only because in this case everything disappears. Right? So what's your conclusion about this? Now we're going to work from our very concrete tools and then back to the abstract setting. Does this matrix have a solution?
No.
No, because this row says that the system is inconsistent. So then that's the same as, do these x, y, and z exist?
No.
No. Which means, can I find some scalars to multiply these guys, which gives me that vector out? No. And that means that I cannot get a general vector in R3 by combining these guys. So R3, so our set 1, 2, 3, 3, 4, 5, 4, 5, 6 is not a spanning set for R3. Now my question is, how on earth is that even possible? I give you 3 vectors. 3 vectors should contain enough information to describe all 3-dimensional space. Right? If I give you a vector pointing this way, and a vector pointing this way, and another vector pointing in the direction of my head, I guarantee you I can combine those 3 vectors to get any point in x, y, z space, right? Go this way for a while, go that way for a while, go this way for a while, you'll get there. So what happened?
They're coplanar.
Is it because there's repeats?
So that's actually the same answer in 2 different sets of words. So there's repeated information. So actually what's going on here is these 3 vectors lie in the same plane. Now there was no way to know that just eyeballing them. This is why linear algebra is hard, right? Those 3 vectors are not obviously coplanar.
Are all 3 of them coplanar?
Yeah,
Or if,
all 3.
If like 2 of them were coplanar and 1
That still would be, sometimes that's enough to break it and sometimes not. In this case, because we had 3 vectors, we've dropped information. If I just give you 2-dimensional set, there's a direction we can't go, which is not enough to get all of R3. I can only go 2 independent directions here, not 3 independent directions. Notice that information was also contained in the row-reduced matrix.
Yo, what does coplanar mean? Because it said in the book. What does that mean?
So what coplanar means is that they lie. If you imagine that you took two of the vectors, so if you took these two, and this was v1, and this is v2, that v3 is a linear combination of v1 and v2. It means that you're not getting any new information because I could write this vector down as a combination of these two. And actually, this tells you the exact combination. This matrix, we're going to get into this in later chapters, tells you these two have all the information, and this one is negative 1/2 of the first vector plus 3/2 of the second.
What would the answer look like if it could, like there would be A's and B's in the...
I can show you that too, yeah. So I have another example where it does actually hit it exactly, and that looks like, do I have it in here? Yep, this one. Okay, so let's do exactly the same question, but this time I'll give you enough information to actually do it. So if I ask you the same exact question, is 1, 0, 0, 0, 1, 0, minus 1/2, 0, 3/2 a spanning set for R3?
Yes.
And I'm going to show you, but let me show you what the augmented matrix looks like so you can see when it's row reduced what the coefficients look like. Yes, the answer is yes because by the logic of math classes, but so if you did the same thing where you wrote down x times 1, 0, 0 plus y times 0, 1, 0 plus z times minus 1/2, 0, 3/2 is equal to an arbitrary vector ABC, and you turn that into a row reduction problem. 0b, 0, 0, 3/2 c. First off, this is going to have a solution this time because you already know there's 3 pivots, right? If you row reduce this, what you end up with is, so this row reduces to 1, 0, 0, 1/2 of 3a plus c, 0, 1, 0, b, 0, 0, 1, 2/3 of c. And so that tells you not only is this consistent, which means there is a way to write down an x, y, and z that makes this equation true, it actually tells you what values you would plug in to do it. So this says if you plugged in x is equal to 1/2 of 3a plus c, and y is equal to b, and z is equal to 2/3 of c, into this spot, and that spot, this equation would become true. And that works for any vector a, b, and c, which means it is a spanning set in this case. Since every vector in R3 can be written as a linear combination of these three, with that particular solution, it is a spanning set. This always has a solution. So 1, 0, 0, 0, 1, 0, minus 1/2, 0, 3/2 spans R3.
So you can pick any value for A, B, and C
You can.
independently, and as long as you feel okay.
Yeah. So any vector in R3 can be written as a linear combination of these guys with those precise entries for the x, y, and z. All right. Now, just to make sure everyone leaves confused, more confused,
Okay, there you go.
I'm going to soften the, there's this old saying, like this mathematician Grothendieck said that you don't solve problems by working hard, you just like soften the walnut, right? You put them in water and they get soft and the solutions fall out. So I'm going to soften the walnuts inside your skulls by giving you a really abstract thing to think about. So, all this crap we've done so far has been about matrices and vectors, which means linear algebra seems really limited, right? Not everything in the world is R2 or R3 and matrix multiplication. So one of the first things that you start studying when you do this is the space of polynomials. So if I wrote down P2 of R, that is fancy notation for this set. It's everything of the form A0 plus A1x plus A2x squared. where A naught, we saw this earlier, A naught, A1, and A2 are real. That's a vector space. If I add polynomials together, I add like terms. It's closed under scalar multiplication. Multiplying by, or under addition, and multiplying by a scalar is not going to suddenly make the degree of the polynomial go up, right? So the abstraction here is to say, you know, this is really no different than the vector A naught, A1, A2. I can record all of the information about that polynomial as a vector space by just throwing the 1, the x, and the x squared away and just keeping the coefficients. And if I call this the 1 spot, and this the x spot, and this the x squared spot, if I give you one of these, I can reconstruct the polynomial it came from. And if I give you a polynomial, I can rewrite it as a column vector. So, one of the most important things that exists in applied mathematics is a set of polynomials used for approximation called Legendre polynomials. So you haven't seen those yet. You take 344, you will. Some of you have in your classes. So L naught is the function 1. L1 is the function x. L2 is the function 3/2 of x squared minus 1/2. Is that familiar?
Nope.
We just wrote them down as column vectors.
Yeah.
So if I write those things down, but I translate them into their column vector versions, this would be the vector
Did we not have plus C?
1, 0, 0. This would be the vector 0, 1, 0. And this would be the vector minus 1/2, 0, 3/2.
Wait.
I'm just recording where the coefficients sit on the powers of x.
Didn't we have plus C from here?
Plus c.
Wait, wasn't x 1/2 3a plus C, or was it not?
No, it was just 3/2 x squared minus 1/2. There was not supposed to be a plus c on it.
No, x equal. Never mind. Oh, never mind.
Scalar term, x squared term. So
Oh,
this-
these aren't the answers. Okay, never
No,
mind.
I haven't answered anything yet. I've not answered anything yet. Now the question, if you're an applied mathematician, might be, is it sufficient for me to study all my second degree polynomials by just expanding them in terms of these? This is a core idea of applied math, is these polynomials have really nice properties. If only every polynomial could be written in terms of them. If only every second order Taylor expansion could be written in terms of these. And so to ask the question is P2 of R spanned by 1x and 3/2 x squared minus 1/2 is literally the same question as asking, is R3 spanned by 1, 0, 0, 0, 1, 0, minus 1/2, 0, 3/2. They are the same question. This is what linear algebra is for. Abstract ideas like, can I build all the second degree polynomials out of these really nice ones, can be turned into questions about column vectors. So, part of the reason why this is going to be hard is because we're going to be playing on sort of both sides of the fence here. There is concrete matrix calculation that we're going to be doing, where everything is row reduction, but we have to be able to translate these abstract questions into this hammer that we have that we can go hit it with row reduction. And that's kind of why the next part of the class is so hard, is to have to be able to move back and forth between these two pictures. I'm going to talk more about this next time. So, see you guys.